All right, continuing where we left off, we were talking about the heat of vaporization for water, which is 540 cals per gram of H2O, or if you convert it into joules, it's 2260 joules per gram of water. Okay. All right, so this conversion factors come into play when we are converting water from one state into another, or any substance. If we have their heat of vaporization and heat of fusion, we are able to convert the whatever amount of substance from one state into another. So for example, you have 50 grams of steam from a volcano, and it condenses at 100 degrees centigrade. All right. So how many kilojoules are released when this happens? Okay. All right. So you've been given 50 grams of steam. You've been given the temperature. It's occurring at 100 degrees centigrade. And you've been asked to find out the kilojoules released. Okay. So when steam condenses to water, liquid water, it requires 2260 joules per gram of H2O. Okay. And so you will take the 50 times the 2260 and get your answer in joules, but then you need the answer in kilojoules. So divide by 1000, and so 3 sig figs, and therefore your answer is 113 kilojoules. A heating curve is where you're looking at the changes of state of any substance. All right. So for example, in water, below zero, it's in solid state. All right. When it gets to zero, it starts melting and it's in the process of becoming liquid. All right. One of the things you will see is that there is a temperature change till it gets to the melting point of 0 degrees centigrade. All right. So on these vertical lines, there are temperature changes occurring as you're supplying it heat. All right. So it's going from -40 to 0. And then the temperature stays constant here at 0. And that's why you see that flat line, the horizontal line or the plateau. The reason for that horizontal line is because the temperature is staying constant at 0 degrees until all of that ice is become water. All right, till all of the ice has melted and become water, the temperature stays constant. And then once it all melts, then the temperature will keep rising till it gets to 100 degrees centigrade. All right, and then again at 100 degrees centigrade, all of that water has to become steam. Till then the temperature will not change. Once all of the water is converted to steam, then again there's a temperature change. All right, so the diagonal lines indicate changes in temperature, the horizontal lines indicate changes in state, okay, where the temperature remains constant. So the plateau or the horizontal line on a heating curve represents a constant temperature and a change of state as well. The sloped line represents a temperature change. Use the cooling curve for water to answer each of the following. All right. So the heating curve was going in one direction. The cooling curve would be, of course, in the opposite direction. All right. So going back to that curve. So this is a heating curve. Now, if it were a cooling curve, it would start out here. All right. So you'll have a vertical line, come to 100, and then a horizontal line, then another vertical line till you get to 0, and then a horizontal line, and then another vertical line. All right. So it's the exact opposite. If you flip this over, that's what you get as the cooling curve. Use the cooling curve for water to answer which of the following. Water condenses at a temperature of 0 degrees, 100 degrees centigrade. What am I saying? So it's boiling at 100 degrees centigrade and also condensing at 100 degrees centigrade. At a temperature of 0 degrees centigrade, liquid water is freezing, all right? Liquid water freezes, solid ice melts. At 40 degrees centigrade, water is a liquid. When water freezes, heat is being removed. So this is the cooling curve, the exact opposite. You're starting with steam. At 100 degrees centigrade, you have water plus steam. So at all the horizontal lines, you have two states. On the vertical lines, it's just one single state, all right? So steam, but here at 100 degrees centigrade, the temperature is constant. You have two states, and then it's water until you get to 0, and then you have water plus ice again at 0, and then below 0 it's ice. So calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees to gas, it's vapor, at boiling point of 78 degrees. Ethanol has a specific heat of 2.46 joules per gram degree centigrade and a heat of vaporization of 841 joules. Okay. All right. So we've been given the specific heat. We've been also given the heat of vaporization. All right. Okay. So first we draw the heating curve, all right? So ethanol at 78 degrees is liquid plus vapor, all right? And I think I've done this incorrectly. Heating curve is going to go the other direction. This plot has to be flipped over. But anyway, you'll kind of get a picture of what's happening. At 78, you have both the liquid and the vapor, two states, and the temperature remains constant, all right? So you use 15 grams and multiply it by 841, the heat of vaporization for ethanol, and you get now I think it was 15.0, so that's why the calories is in 3 sig figs, the joules is in 3 sig figs. So you get 12,600 joules, 3 sig figs. And then next is ethanol 25 to 75, all right? So that change to 78 rather. So 78 minus 25, that change delta T is 53, all right? It's 15 grams mass times the change in temperature times the specific heat of ethanol was given as 2.46 joules per gram degree centigrade. So that gives you 1960 joules, all right? So this is the joules from going from 25 to 78. This is the state change, and so you add up both together and you get 14,600 joules, all right? So you add up 12,600 plus 1,960 and you get 14,600 joules, all right? And if they asked you for kilojoules, you just divide it by 1,000, so it'll be 14.6 kilojoules. All right, so the temperature change was 53. So 15 times 53 times the specific heat of ethanol, so 1,960 joules. The next step is converting the liquid ethanol into vapor. So that takes 840 joules per gram. So it's 12,600 joules. So you'll add the 1960 plus 12,600 to get the total heat needed, which comes out to be 14,600. Okay, in this study check, a volcano is erupting and you get 175 grams of steam at 100 degrees centigrade. How many kilojoules are lost when the steam condenses and then freezes at 0 degrees centigrade? So you have 175 grams of steam at 100 degrees centigrade, and then it condenses and freezes when it becomes ice at 0 degrees centigrade. Heat of vaporization is 2260 joules per gram for H2O. Specific heat is 4.184 joules per gram degree centigrade, and heat of fusion is 334 joules per gram. All right. So you have to take a cooling curve in this case. So it'll be 175 grams of steam, and you have to convert it into joules. So you'll multiply by the 2260. This is happening at 100 degrees, so the temperature is not changing. And then once you've converted it into liquid water, then you have a temperature change to 0 degrees. So then it's going to be 175 times the 0 times the 100, because you're going from 100 to 0, times the 100 times the 4.184. All right, and that will give you your answer in joules. The next is, once you've gotten to 0, you have to make it ice. All right, so you have to take the 175 grams of liquid water and make it into ice. So then you'll multiply by 334. So it'll look something like this. Here it's going to be 175 times the 2260, and on this vertical line it's going to be 175 times 100, because it's going from 100 to 0. So times 100 times 4.184, and then here it's going to be 175 times the 334. Okay, so these are all your conversion factors. So the first step is converting all of the steam into liquid water. So 175 times the 2260, and you get 396,000 joules. Okay, the temperature change was 100, and so 175 times 100 times 4.184, and you get 73,200 joules. And then the final step was taking all of that liquid water and converting it into ice. So times 334, and that gives you 5,500 joules. So now you'll add them all up, the 396,000 plus the 73,200 joules, and then the 58,500, to give you a total of 528,000 joules divided by 1,000, and you get 528 kilojoules. Okay, so therefore the answer among the choices given would be B. Right, so that's the end of this chapter 3. So we started out by looking at matter, defining matter as being mass and volume, and the states of matter: solid, liquid, and gas, and then classifying the matter into pure substances and mixtures. Pure is elements and compounds. Mixtures are homogeneous, where they're uniformly distributed, the components of the mixture, or heterogeneous, where you can actually see the different phases of the components. All right, and then we talked about change of state and heat in calories and joules, specific heat, and melting, freezing, heat of fusion, heat of vaporization, and we finally looked at heating and cooling curves. And that's the end of this chapter.